So as we talked about before, the double convex is the standard. And we'll see how that works here when we talk about another lens. So the double convex is the standard. And so because it is the standard, then the direction for our object distance, our focus, and our image distance, these are considered positive orientation. So we need to remember that's a little different from the mirrors, but we need to keep track of how with the double convex, our object distance is on one side and the focal distance and the image distance are on the other side of the lens. So now let us come up with an equation for this where the image distance is going to be in relation to the focus and the object. And the first thing we notice is that we have some similar triangles. We have FI, I prime, is a similar triangle to FAB. And B is just an extension of the parallel line from the object over to the center line of the lens. And because we have excuse me, similar triangles, we can have the equation, or the proportions, our image height over our object height is equal to our image distance minus the focus, that's just this distance here, divided by our focus, this line here. Now, the other triangles that we see are similar. We have OA, O prime is similar to the triangle IA, I prime. And we now have the relationship, our image height over our object height is equal to our image distance divided by our object distance. And putting these two expressions together, and simplifying these, I'll let you do this on your own. I did it last chapter. You should see how to do it. We get 1 over our object distance plus 1 over our image distance is equal to 1 over the focal distance. And the surprising thing is that this equation is the same as what we had for the mirror. But remember, it only works when you use the positive orientation. With the mirrors, the focus and the digital image distance were on the same side as the object distance. Here with the lens, we have to remember the difference, but the equation is the same. That's the interesting part. Now, let's look at our system here where we have a double concave lens, and let's do the same kind of analysis as we did for the double convex and see what we get. Well, the first thing we notice is that we have similar triangles of IA, I prime. And that is similar with the triangle OA O prime, which leads us to the equation, our image height over our object height is equal to our image distance over our object distance. Then we have IF I prime, this triangle, and that triangle is similar to IA, or I'm sorry, AFB, this triangle here. Those two are similar. And that gives us the equation of our object height over, or I'm sorry, our image height over our object height is equal to the focus length minus the image distance divided by our focal length. And if we take and simplify this, we get 1 over our object distance minus 1 over our image distance is equal to the negative of the focal length. Now here's the interesting part that helps us to really see we can only need one equation here, is let's look at these. With the double convex, my image distance and my focal length are positive on the right-hand side of the lens. But when I look at the double concave, the focal point and the image are on the left side, in a sense, in the negative position. So here, notice that DI is negative, your focus is negative. So this is just the same thing as saying 1 over DO plus 1 over negative DI, our image distance, is equal to 1 over our negative focus. So if we use the double convex as our positive orientation, then we know that when we do a double concave, that our image distance and our focal distance are going to be negative, and we can use the same equation as we have for the double convex. It becomes our standard, and we just put in positive and negative values for our image distance and focal distance based on the lens that we're going to use. So this really makes it easy for us to be able to solve problems because it's just really one equation.